Right, so now in section 8.3 we're going to be doing rational functions and their graphs. And when we work with these rational functions, they could be linear functions in the numerator denominator, they could be quadratics, they could be cubics. So what's going to happen is our graphs are going to be looking like nothing you've ever seen before, because we're going to have continuous graphs and we're going to have non-continuous graphs. We're going to have points that we're going to remove. We might have 2 or 3 vertical asymptotes. We might have a horizontal asymptote. You might have graphs going in that direction, in that direction, in that direction, all at the same time. It all depends on what we end up with. Now, just a review of what some of these terms are. Whenever we have a continuous graph, a continuous graph means that we can put our pencil down here and we can draw this line out, and we never have to pick our pencil up, or we never have to pick the marker up or anything like that. When we have a non-continuous graph, that means at some point we've got to pick the pen or the pencil up. So you can see here, because I've got asymptotes, if I want to go to the other part of the graph, I then have to do this right here. I would have to start over again. And then notice that I've got a hole here. This is something that we've never seen before. This is what we call a point of discontinuity. And your other type of discontinuity is an asymptote, which we've been working with, but this is the first time that you're ever going to have seen holes. Now, points of discontinuity, there are again 2 types. There are holes and there are asymptotes. Holes are what we call a removable discontinuity. Asymptotes are what we call a non-removable discontinuity. To determine whether it's a removable or non-removable, we actually have to go back and we have to look at the equation and see if any of our factors, so if we've got a quadratic equation or a quadratic expression and we can factor it down, if we can remove any of those factors, then that would become a removable discontinuity. If we can't remove any of those factors, and those factors are in the denominator, and then they become a restriction on the domain, then that means that they are what we call a non-removable discontinuity. So that's when we get our vertical asymptotes. Here we are in problem number 1. And problem number 1 is split into 3 different problems. We've got problem 1a, which is y equals x plus 3 over x squared minus 4x plus 3. And what we're being asked to do is to find the domain of the function, to find the points of discontinuity, which ones are removable, which ones are non-removable, to identify the x-intercept, and to identify the y-intercept. So what we're going to do here is we're going to look at first the domain of the function. The domain is going to be all real numbers except any restrictions on the x value. And the way that we're going to find the restrictions on the x value is by looking at the denominator. Because remember that when you have a fraction, the denominator cannot be 0, because that would make the fraction undefined. So what we're going to do to figure out what the restrictions are is we're going to have to take this and factor this. So the first thing that we want to do is go ahead and rewrite this to factor the denominator. So we get y equals x plus 3 over x minus 3 times x minus 1. So again, just to check this to make sure that we're correct, x squared, negative 3x, negative 1x, negative 4x, and then negative 3 times negative 1 is positive 3. So this is the correct factorization for this problem. Now, what we see here is we've got x minus 3 and x minus 1. Apply the zero product property to this, and then you would get x is equal to 3 and x is equal to 1. So what would happen if we put 3 or 1 back into that denominator? If we did that, we can just use the factored form here. 3 minus 3 is 0. Then we're multiplying 0 against the other factor, so that means that we would have 0 in the denominator. That's why 3 cannot be one of the x's. Then if we plug 1 into this one, 1 minus 1 is 0, and if you multiply that against the other factor, you would end up with 0. So that's why we can't have either 3 or 1 in the domain. So the domain is going to be all real numbers, and then x cannot be 1 or 3. So that's our domain. Now the next thing we're looking for is removable discontinuities. So removable discontinuities means this: can we cancel out anything in the numerator and denominator? So we look at the numerator and it says x plus 3. The closest thing we've got in the denominator is x minus 3, but we can't cancel those out. So that means that neither of these are removable discontinuities. So we would just go ahead and put none there. Now, as far as non-removable discontinuities, we have two of them. We have one at x equals 1 and one at x equals 3. So it's the same thing as our domain. Then the x-intercept, the way that we're going to find this is we're going to take the numerator and we're going to set the numerator equal to 0. So x plus 3 equals 0, so x equals negative 3. So the x-intercept is going to be at x equals negative 3. Then the y-intercept, remember the definition of a y-intercept is simply the value of y when x is equal to 0. So all we do to find the y-intercept is we plug in zeros for all of our x values. So to do that, we get 0 plus 3 over 0 minus 3 times 0 minus 1. So 0 plus 3 is 3. 0 minus 3 is negative 3. 0 minus 1 is negative 1. So negative 3 times negative 1 is 3. So we would get 1. So the y-intercept is going to be at y equals 1. This is how we're going to do all of the problems here. So let's go ahead and take a look at problem number 1b. We've got x minus 5 over x squared plus 1. Now, if this were x squared minus 1, it would be difference of squares, and we'd have x plus 1 times x minus 1. But since we have x squared plus 1, we would actually end up with imaginary numbers. So we can't do any sort of factoring on the denominator here. So because we can't do any sort of factoring the denominator, and we know that there's no way for us to get a negative 1 here, because if we're squaring any number, we're going to get a positive. So that means that there's no way that we can make that denominator equal to 0. So that means that the domain is going to be all real numbers. Then we're looking at removable discontinuities. And again, we don't have any factorization, so there are no removable discontinuities and there are no non-removable discontinuities. So we're going to have none for both of those. Then for x-intercepts, we're going to take that x minus 5 and set it equal to 0. So x is equal to 5, and so we get an x-intercept that is equal to 5. The y-intercept, same as we did over here. We know that the y-intercept is the value of y when x is equal to 0. So we're going to plug in 0 for all of our x's. So 0 minus 5 over 0 squared plus 1. And we get negative 5 over 1 or negative 5. So our y-intercept is at y equals negative 5. Last problem, x squared minus 3x minus 4 over x minus 4. So on this one, again, we've already got this one factored down. It's linear. So we know that if we were to take 4 and plug that in for x, that we would get a 0 in the denominator. So that's going to be our one restriction on the domain. So the domain is going to be all real numbers with x cannot be equal to 4. Then we're going to look for removable discontinuities. But before we can do that, we've got to factor the numerator. So we get y equals, and then x minus 4 times x plus 1 over x minus 4. So again, just check this real quick. X times x is x squared. 1x, negative 4x gives us negative 3x. Negative 4 times 1 is negative 4. So we know that we've done that correctly. Now we can see that we've got an x minus 4 in the numerator and we have an x minus 4 in the denominator. What that tells us, we can take this and we can cancel those out. So now we're left with just y equals x plus 1. So our removable discontinuities are going to be at x equals 4. We don't have any non-removable discontinuities because we don't have anything left in the denominator. So that's going to be none. Now our x-intercept, we set x plus 1 equal to 0, and that gives us x equals negative 1. So our x-intercept is at x equals negative 1. Again, for the y-intercept, just go ahead and plug 0 in for everything. And so you get 0, 0, negative 4. So negative 4 over 0 minus 4 is negative 4. So negative 4 over negative 4 is 1. So we get y equals 1. And that is going to be how you look for or check for any discontinuities, both removable and non-removable. For problem number 2, we're going to build on what we just did in problem number 1. In problem number 1, we found the removable and non-removable discontinuities. And so we're going to see how a removable or non-removable discontinuity affects the graph. Remember that removable is the same thing as a hole, and non-removable is the same thing as a vertical asymptote. So in problem 2, we're given y equals x plus 1 over x minus 2 times x minus 3. And we're asked to find what are the vertical asymptotes of this particular equation. So we're going to look at this and see if we can remove anything. And to remove anything, we'd have to have an x plus 1 in both the numerator and denominator, which we don't have. So that means that both factors in the denominator are non-removable factors. Because they're both non-removable, this means that they're both going to be vertical asymptotes. So the way that we figure out what they're going to be, or where the vertical asymptotes are going to be located at, is to use the zero product property on both of those factors. So we go x minus 2 equals 0, and x minus 3 equals 0. At this point, you should be able to do this without doing any work. X equals 2, and x equals 3. That is where your vertical asymptotes are going to be. So if you were to graph this, then you would go to 1, 2, and 3, and you would put vertical asymptote at 2 and a vertical asymptote at 3. That's where your graph is not going to be able to go. Now for problems 3a through 3c, we're going to look to see if we can figure out what the horizontal asymptote is. So we've got y equals 2x over x minus 3 in 3a. So we're going to look again at what are the degrees of the numerator and denominator. So up here, we've got an x to the first, and down here we've got an x to the first as well. So go back to the rules, which tells you anytime that m equals n, the horizontal asymptote is going to be a over b. So we've got, again, a 1 and a 1, which means that the horizontal asymptote is going to be the lead coefficient over the lead coefficient. So 2 over 1, or y equals 2. Going over to 3b, we've got x minus 2 over x squared minus 2x minus 3. So in this case, the value of m is 1, the value of n is 2, and so we're going to be looking at m is less than n. So anytime that m is less than n, we know that we automatically have a horizontal asymptote at y equals 0. For the last one, we've got y equals x squared over 2x minus 5. So in this case, the degree of the numerator is 2, and the degree of the denominator is 1. So we've got m is greater than n in this case, which tells us that there is no horizontal asymptote for that particular problem. Before we move on to problem number 3, we've got to look at how we calculate the horizontal asymptote whenever we're dealing with any of these rational functions. So the way that we're going to do this is we're going to look at two things. We've got the lead coefficient, which is going to be a in the numerator, and the lead coefficient, which is going to be b in the denominator. Now, what I'm going to term the lead exponent, so the highest exponent in the numerator, we're going to call m. And then the lead exponent in the denominator, we're going to call n. This just gives you the degree of that particular numerator or that particular denominator. So if you had x squared plus 1 in the numerator, then it would be second degree. If you had x cubed minus 1 in the denominator, then it would be third degree. So what we're looking for is the relationship between m and n. If m is less than n, then the horizontal asymptote is going to be at y equals 0. If m is greater than n, so if the degree of the numerator is greater than the degree of the denominator, then you're not going to have any horizontal asymptote. But if the degree of the numerator is equal to the degree of the denominator, then the way that you're going to calculate the horizontal asymptote is by taking the lead coefficient over the lead coefficient, so a over b. So if this were 3x squared and 4x squared, then it would be 3 over 4. That would be your horizontal asymptote. In problem number 4, we're going to take everything that we've learned and we're going to apply it to graphing one of these rational functions. So we're given y equals x squared plus x minus 12 over x squared minus 4. And what we're going to do is we're going to produce this entire list of items. So we want to say, what is the factored form? What are the points of discontinuity, which double as your restrictions on x? Where are the holes at? What are the vertical asymptotes? What are the horizontal asymptotes? What is the y-intercept, the x-intercept, the domain, and the range? So the first thing that we're looking at is the factored form. So we want to factor x squared plus x minus 12. So what are the factors of 12 that subtract to 1? We get 4 and we get 3. So it's going to be x plus 4, so y equals x plus 4 times x minus 3 over, and then this is just going to be a difference of squares. So x plus 2 times x minus 2. All right, let's check that, just make sure that we've done it correctly. X times x is x squared. Negative 3x, positive 4x, that gives you x. 4 times negative 3 is negative 12. Difference of squares, we got that. Now, points of discontinuity. What would make x plus 2, or what would make x plus 2 equal to 0? That would be a negative 2. What would make x minus 2 equal to 0? That would be a positive 2. So we know that we have points of discontinuity at plus or minus 2, or x equals plus or minus 2. Now, are any of these going to be removable, or are they all going to be non-removable? X plus 4 and x minus 3, we cannot remove anything out of the denominator with those two factors. So that means that we don't have any holes in this particular graph. But we are going to have two vertical asymptotes. Those vertical asymptotes are going to come at x equals plus or minus 2. So what I'm going to do is I'm going to go over here, and on here I'm going to go ahead and draw in a dashed line at negative 2 and a dashed line that signifies 2. So what I'm going to have to do is find some points in between, or to the left of negative 2, in between negative 2 and 2, and then to the right of 2 in order to be able to fill this graph out. Now the horizontal asymptote. I'm going to go back up to the original here, and I can see that m is equal to n. So since m is equal to n, that means that I've got to do a over b. A is 1, b is 1, so we get a horizontal asymptote of 1, or y equals 1. So I'm going to real quickly just change that up to y equals 1. Now I'm going to come over here to the graph, and I'm going to start filling all of this stuff in that I've got. So I know that I've got a horizontal asymptote at y equals 1. I've got a vertical asymptote at x equals negative 2. And I've got another vertical asymptote at x equals 2. And so you can see now that I'm going to have, most likely going to have something here, and then something here. If it were a negative, then it would probably be here, here, and here. Now looking for the y-intercept. Remember that the y-intercept is simply going to be the value of y when x equals 0. So go in here and plug in 0 for each of your x's. So you get 0 plus 0 minus 12, so negative 12, over 0 minus 4, negative 4. And so I know that the y-intercept is going to be at 3. So I can come over here to this, and I can graph 3 on here. Okay. Then I'm going to go to the x-intercept. So I'm going to figure out where my x-intercept's at. So the x-intercepts, again, are going to be setting this equal to, setting each of those equal to 0. So x plus 4 equals 0 gives you x equals negative 4. And x minus 3 equals 0 gives you 3. So I can go over here and I can put in an x-intercept at 3 and an x-intercept at negative 4. I can also go through here and I can say that I've got 0, 3, and I've got negative 4, 0, and I've got 3, 0. So I've already filled in some of the things on my chart just by finding this information. Now the domain. What cannot be in the domain? The only things that can't be in the domain are plus or minus 2. So we're going to say all real numbers with the exception x cannot be plus or minus 2. The range, the only thing that can't be in the range is y equals 1. So we're going to say real numbers, all real numbers, y cannot be equal to 1. Okay? So all that's left now is to fill in this chart and then to graph the points that I come up with. So to do that, let's pick some points. Let's go to -3. Let's go -5. Let's go to -1, 1. We've already got 3 and 0, so let's go ahead and slide this up here to there and there. 4 and then 5. And so what I'll have is 3 points in each of these sectors of the graph, and that'll start to give me an idea of what this graph is going to look like. So sometimes the easiest way to do this is to go and plug each of these numbers into the factors that you've got here. So for -5, we're going to get -1 times -8 over -3 times -7. So we've got 8 over 21. So we're going to put -5 is 8 over 21. Then -3, we would end up with 1 and 0. Or I'm sorry, -6. So 1 and -6 over -3 plus 2 is -1. And -3 minus 2 is -5. So we get -6 over 5. So we'll put that right there. Then on the next one, we've got -1. -1 plus 4 is going to give us 3. -1 minus 3 is going to give us -4. Over -1 plus 2 is 1. And -1 minus 2 is -3. So we get -12 over -3, which gives us 4. So we'll put 4 in right there. Then we've got 1, so we'll go 1 plus 4 is 5. 1 minus 3 is -2. Over 1 plus 2 is 3. And 1 minus 2 is -1. So -10 over -3, which gives us 10 over 3. So we've only got a couple more left to go here. We got 4. 4 plus 4 is 8. 4 minus 3 is 1. Over 4 plus 2 is 6. And then 4 minus 2 is 2. So we get 8 over 12, which reduces to 2 over 3. And our last one here, we've got 5, so 5 plus 4 is 9. And 5 minus 3 is 2. Over 5 plus 2 is 7. And 5 minus 2 is 3. So we get 18 over 21, which reduces to 6 over 7. Okay, now we can go and we can plot these. So -5 and then 8 over 21. So let's see, we've got -1, 2, 3, 4, 5, and then 8 over 21 is going to be roughly 1/3. So we'll put a point in there. We've already got -4, 0, -3, and -6/5. So -6/5 is just a little bit greater than 1. So we can see that we've got, that is the left part of our graph. Now for -1, we've got 4. So 1, 2, 3, 4. Oh, we've got to change this up just a little bit. Accidentally put that in at 4 instead of 3. So then go to -1 and 4. And 1 and 10/3. So that's going to be 1 and 3 and 1/3. So it's, what you can see is that this center section here is not going to be a parabola, because it's not going to be something that's symmetrical. It's not going to be perfectly on top of itself. So what we're instead going to have is a funky little looking parabola that looks like that. Then finally, we've got 3 and 0, which is already on here. 4 and 2/3. So 4 and 2/3 is going to be right about there. and then 5 6/7 is going to be right about there. If we really wanted to make this a graph, a really accurate graph, what we could do is we could go in here to 2.5 and we could figure out what 2.5 is. But I'm not going to get that picky on this question. I'm just going to go ahead, and I know that it can't bump up against that vertical asymptote, so it's just going to get closer and closer and closer. This is what your graph is going to look like on this particular rational function.